Okay, we're back with some notes on the difference between speed and velocity. And this is a case, it's kind of similar to distance and displacement. In everyday language, we say that distance and displacement, we use them interchangeably, okay? But in physics, they mean different things. I heard it once said that physics is learning physics is like learning a foreign language that sounds exactly like English, but some of the words mean differently or have different meanings than you are used to, okay? We know that distance and displacement sound similar, but we know that they're not the same thing. We also know that speed and velocity are not the same thing. Even though we use them the same in everyday language, in physics, they're not the same. Let me define both of them for you. We spent last video talking about how speed was, one way to define it, was the change in distance over a change in time, okay? So basically, how far something traveled over a period of time. Another way to say this, because we're looking for a change in something, we often like to use the phrase rate of change. Speed is the rate of change of distance over a period of time. Okay, the rate of change of distance over a period of time. And the equation is that speed equals distance divided by time. Very predictable. Now the difference between speed and velocity hinges on the difference between distance and displacement. Velocity, instead of being the rate of change of distance over a period of time, is the rate of change of displacement over a period of time. And the equation is velocity equals displacement over time. Okay? So remember that distance just means the total path length, regardless of direction. Okay? So when we calculate speed, we are simply just looking for how fast something is moving. How much distance is it covering over a period of time? Since the direction doesn't matter for distance, it doesn't matter for speed either. And remember that any measurement where the direction doesn't matter is referred to as a scalar measurement, S-C-A-L-A-R. Velocity, on the other hand, is the rate of change of displacement over a period of time. Velocity is not just how fast you're moving. Velocity is how fast are you getting away, or at what rate are you getting away from your initial position. That's what velocity shows you, okay? Displacement over time, change in displacement over time. Because remember, displacement is where are you, how far away are you, and in what direction from your starting point. So when we talk about velocity, we're essentially saying, okay, over the course of this motion, at what average rate did the object move away from its starting point? Since we're dealing with displacement, and displacement is a vector, the direction matters, velocity also has the direction matter. Therefore, it is a vector quantity. And again, the difference, so there's really two differences between speed and velocity. Speed is a scalar, velocity is a vector. Notice that they start with the same letter, speed, scalar, velocity, vector. That's great. The other difference is that one is distance over time, that's speed. The other is equal to displacement over time, that's velocity. The tricky thing, and you'll notice this on the reference tables, is that both of them are given by this equation. V hat equals d over t. We do not differentiate displacement from distance. Both of them are d. You'll see that if you look at the reference tables. The same thing with v. You'll see that it either means speed or velocity. It is up to you to know the context of the problem. Okay? I'm sorry that it's like that, but that's just the way it is. The difference between speed and velocity stems from the difference between, as I said, the distance that an object travels and its displacement over some period of time. Okay? Those two things are different, but they can be the same. When these two quantities are the same, speed and velocity will also be the same. When they are different, speed and velocity will be different. So it all hinges on how distance and displacement compare to each other. If they're the same, speed and velocity are going to be the same. If they're different, then speed and velocity are going to be different. Think about the only situation in which distance and displacement will be equal. If you think about that, when is the total length of the path an object travels, the distance, equal to how far away the object gets? Well, if you think about it, if distance is the total path length and displacement is just how far is it from where it started, The only way those can be equal to each other is if you have an object that travels in a straight line. Or I guess doesn't travel at all, but assuming the object moves, the only way those can be equal is for an object that travels in a straight line without changing direction, without turning around, without any change in direction. Okay, so the only situation where they can be the same is motion in a straight line with no turning around or changes in direction. Okay, think about it. If you have an object that's moving in a straight line, then the length of that path is just the length of that straight line. And displacement is the straight line length between starting and ending points. So that's fine. If you have an object that starts to turn, if you're not going straight away from where you started, now your displacement is not going to be as long as the path length. Even if you turn 100% around, or by 180 degrees, and you start going back towards the origin, that just means you're decreasing the displacement over this period of time, but the distance is still increasing because the path length is still getting bigger. You have to go all the way out and then back in. Okay? So you need to remember that motion in a straight line with no turns at all is when distance is equal to the displacement. We're just going to go through a whole bunch of examples now to illustrate this. So, first example, a car travels 7 kilometers south down a straight level road in 300 seconds. Find the average speed and the average velocity. The straight level road part is very important, but I'll come back to that in a second. First thing we want to do is we want to find the average speed. So I'm going to use my equation, v equals d over t, and I'm just going to put in parentheses that we're finding the speed with this one. Okay? So, the speed is equal to the distance traveled over the time. The car travels, the length of its path is 7 kilometers. So I'm going to write, okay, well actually I could probably do this in my head. Let's change it to meters per second. 7 kilometers, we know kilometers is 1,000 meters. You can write the unit conversion if you want, but I know that 7 times 1,000 is going to give us 7,000 meters. In 300 seconds, comes out to be 23.33 meters per second. Okay, that is the speed. Now, in this situation, does the object travel in a straight line without turning? Yes, it says straight level road. There's no change in direction here. So we can conclude that the distance must be equal to the displacement. So the velocity is also equal to 23.33 meters per second. Or maybe I should say the magnitude of the velocity is 23.33 meters per second. Because something's missing. I do need one extra bit of information if I'm solving for the velocity. Remember, velocity is a vector. All vectors need to be described by both their magnitude and their direction. What that means is we need to know in what direction was the velocity. Well, that's easy. In what direction was the displacement? The car is traveling to the south, so the car is being displaced to the south, so the velocity of the car must be directed south. We do need to include that to make our answer complete. The average velocity is 23.33 meters per second south. Okay, so straight line motion, no turning around. Distance is equal to displacement, so the speed is equal to the velocity. I'll include that right there. Number 2. A little bunny rabbit is hopping away from a wolf. It hops 30 meters north, and then to confuse the wolf, changes direction and hops 60 meters west. So we got like this. It takes the little bunny rabbit 35 seconds to complete this entire motion. A, what is the average speed of the little bunny rabbit? Okay, since we're looking for speed, I just need distance over time. The distance here would be given by simply adding up the total path length. 30 meters one direction, 60 meters the other direction. That's a total, I'm going to show the math actually, 30 meters plus 60 meters, that's going to add to be 90. This whole thing takes 35 seconds to happen. So 30 plus 60, that's 90, divided by 35. Ooh, 90 divided by 35, there we go. 2.57 meters per second is the average speed. Now, do I need a direction on this? No, because I'm solving for the average speed. On the other hand, the displacement is a little trickier. The reason the displacement's trickier is because I need to figure out how far away the rabbit is from where he started. Okay? At the end of the 35 seconds, he's here. He started here. How big is... Oh, bad drawing. How big is that? How big is the length from here to here? And you might say, wait a second, that looks like a right triangle, and you're absolutely right. This is a right triangle with legs of 30 meters and 60 meters. I can solve for x by using the Pythagorean theorem. A squared, maybe I should call it c. You guys are used to that. A squared plus b squared equals c squared would allow me to use 30 meters squared plus 60 meters squared equals c squared. I can do this math very quickly. 30 squared is 900. 60 squared is 3600. I add those together. I get 4500. I take the square root, and I find out that c, which is our displacement, it's how far the rabbit is. It's just the magnitude of the displacement, I suppose. It's how far the rabbit is from where he started, is 67.08 meters. And you could give a direction if you wanted to, but I'm not going to get into all that. If the question asks for the direction, you do have to do it. This is in kind of a northwesterly direction. You can find the angle, but I'm going to skip over that part if that's all right with you. Okay, so let's see here. Now we find the velocity by doing the displacement over the time. The displacement is, as we just found, 67.08 meters. The time is 35 seconds. I'll label this the speed. The velocity, therefore, is 1.92 meters per second. Now, you might look at that and say, how can the velocity be different from the speed? Remember the definitions. Speed is just the total, is how fast you go over the path length, okay? The rabbit covered approximately 2.57 meters per second, all right, as he was moving. The velocity, on the other hand, is the rate at which the rabbit moves away from his initial position. Even though he moved farther, he had a large path length. Because he changed direction over the course of its motion, over the course of the rabbit's motion, because the displacement is smaller than the distance, the velocity is actually smaller than the speed. So the rate at which the rabbit was, on average, moving away from its starting point was a little bit less. Okay, and that's a tough distinction to make, but you got to get used to it. All right, a couple more problems. Number 3. A runner is running on a circular track. It takes her 35 seconds to run halfway around the track, which has a radius of 30 meters. A, what is the runner's average speed? And then B, what is the average velocity? Okay, runner's average speed, that should be pretty easy. We need V equals D over T. But how am I supposed to figure out how far the path length, the distance is from starting point to end point? Notice it's a circular track. You should remember that the distance around a circle is known as the circumference, and there's an equation for that. The circumference is 2 pi r. Well, this is only half a circle. So what's 2 pi r divided by 2? You just cancel out the 2's. The distance ends up being pi times r. So the distance here is equal to pi times the radius, which is 30 meters. And we're not going to leave this in terms of pi. That's kind of lazy. Okay? The distance is 30 times pi. So it's 94.25 meters to go halfway around the track. Okay, that's the path length. The speed is the distance over the time. The distance is 94.25 meters. The time is 35 seconds. And I end up with a speed of 2.69 meters per second. Okay, that's how fast this runner was covering distance. The average velocity is a little, well, actually, it's actually going to be easier this time. We don't have to make a complicated calculation. The displacement is how far the runner is from the starting point at its ending point. That just means finding this. What is the word for that line that I just drew? It is the diameter. The displacement in this case is equal to the diameter which is equal to 2 times the radius. Okay? So if that's equal to 2 times the radius, then the displacement must be 2 times 30 meters, and it's 60 meters. So the velocity is the displacement over the time, which is 60 meters multiplied or divided by 35 seconds. And that would be 1.71 meters per second. And I guess if we took north to be this direction, the runner is ultimately moving to the north. That's how they're displaced. So we could say that the velocity is north. Okay. All right. So again, we see that if it's not straight line motion, the speed is greater than the velocity. And that's always going to be true if there's not straight line motion. There's no way for the displacement to ever be bigger than the distance, because the distance is the entire path length. The displacement is simply how far you are from where you started. The only way for displacement to ever be bigger than the distance is for an object to teleport, and we don't know how to do that with objects yet. Question number 4. A volleyball player is doing sprints. She sprints from one end of the court to the other and then sprints back. The court is 30 meters long. It takes her 4 seconds to sprint from her starting point to the other side. Her average speed on the way back is 6 meters per second. So here's the court. The volleyball player runs to one side and then runs back. Okay? So A, let's just start answering these questions. After 4 seconds, what is the player's distance and displacement? Well, after 4 seconds, she's only made it from her starting point to the other side. So she's running a straight line. What that means is that her distance must be equal to her displacement. So I'm going to write down distance equals displacement. How far has she run in the first 4 seconds? Well, the court's 30 meters long. She went from one side to the next. That means her distance and displacement are both 30 meters. B asks, after finishing the sprint, what is the player's distance and displacement? Well, after finishing the sprint, the path length has doubled. She ran 30 meters to one side, then 30 meters back. So the distance that she has traveled is 30 meters plus 30 meters, so that's 60 meters. What about the displacement? Remember, displacement is how far you are at the ending point from the starting point. Well, if she ran all the way down and then all the way back, isn't she in the same spot that she started in? Absolutely. So that means her displacement is actually 0 meters. She has not displaced herself. She's back in the spot where she started. C asks for the average speed from the beginning to the other side. So that's just from here to here. We know that it takes her 4 seconds to sprint from her starting point to the other side. We also know the court is 30 meters long. That's the distance. That's the time. I have an equation right here. Average speed equals distance over time. Okay? I know that the distance is 30 meters. I know that the time is 4 seconds. If I divide those, I get 7.5 meters per second is equal to the average speed, just to go to the other side. D asks, how much time does it take to get back from the other side back to the beginning? This one's a little complicated because we're not solving. It's not quite clear what we're solving for. We need to know how much time it takes. Okay, I do know the average speed on the way back is 6 meters per second, and I also know that the distance covered in going from the far side back to where she started is another 30 meters. So I'm going to see if I can figure out, based on my average speed equation, the time that it takes. The velocity, or her average speed, is 6 meters per second on the way back. The distance she covers is 30 meters, and we're looking for t. Now be really careful here because it's really easy to solve for t wrongly in this case. What I'm going to do is I can't just divide the 30 to the other side because then I'd be solving for 1 over t. I have a fraction here, I have t on the bottom, I want to get t away from that. That means I'm going to multiply both sides by t. What that's going to give me is 6t equals 30. Now I will simply get the t by itself, and I end up with t equals 5 seconds. And let's see if that makes sense. Does it make sense for a 5 to be down here? Yes, because 30 divided by 5 would be equal to 6. So the time for the player to get back is 5 seconds, 1 second more than it took her to get to the far side to begin with. Part E asks, what is the average speed of the player over the course of the entire sprint? Well, this is pretty easy. If we're looking for average speed, we know that that's just distance over time. The distance that she covers to here is 30, and back is 60, so that's got to be 60 meters. The total time is the first 4 seconds to go here, and then 5 seconds to go back. 4 plus 5, 4 seconds plus 5 seconds equals 9 seconds. We divide 60 by 9, and we get her average speed is 6.67 meters per second for the speed. What about the velocity? Remember, the difference with velocity is that we're talking about displacement now, okay? So the displacement over the time. But this actually ends up being pretty easy because we know the displacement is just 0 over the course of the entire sprint. Not in the beginning, but over the course of the entire sprint. The displacement is 0. The time is another 9 seconds, okay? It's still 9 seconds for her to finish the sprint, so that's still the time. But this means that the velocity is 0. And that doesn't mean she didn't move, it just means that over the course of her motion, she ended up back where she started. The displacement was 0, therefore the velocity was 0. Okay? It's very common to get questions like these that all kind of have very similar questions kind of building off of one another. The last question we're going to go over is a tough one, okay? This is probably not quite AP level, but it's definitely above a Regents level, but I like to talk about it anyways because it's an interesting problem-solving question. A bee leaves the hive and travels for 30 minutes with an average speed of 0.8 meters per second. At the end of this period, its average velocity is 0.45 meters per second. The bee flew in a straight line at the beginning of its flight, then turned around and flew back towards the hive. No other turns were made. At the end of this period, how far is the bee from the farthest point away from the hive that it reached? So there's a lot of information to unpack here. First thing I think I'm going to do is, since my speeds are in meters per second, I'm going to convert 30 minutes to seconds. So I have 30 minutes. I know that there are, let's see, 1 minute, 60 seconds. So this is 1,800 seconds. Okay, in 1,800 seconds, that's how long we're dealing with here. We are told that the average speed is 0.8. 0.8 meters per second equals the distance divided by the total time of flight. Now, is that 1,800 seconds that we just found? That means the distance is equal to, let's see, I just have to multiply these together. I multiply both sides by 1,800. I get 1,440 meters. The velocity, on the other hand, let me make sure you can read this. Okay, yep, looks good. The velocity, on the other hand, is a little bit different. That is 0.45 meters over the course of 1,800 seconds. So the displacement is 810 meters. Okay? Now, I'm going to draw a little picture of what happened. We have the bee flying from the hive all the way out here, and then at some point he turns and flies back towards the hive. It doesn't say he reached the hive. It says he flies back towards the hive. Now, what we know is that the total length of this path, the distance, is 1,440 meters. All of this. The displacement from start to finish is 810. So this right here is 810 meters. Okay? That's how far the bee is from where he started. What we want to know is how far is the bee, not from where he started, but from the farthest point away from the hive that it reached. We want to know how far this is. Okay? Well, if the whole thing is 1,440 meters, and we subtract off the 810 meters that he's still away, that gives us 1,440 minus 810. That gives us 630 meters. Now that doesn't mean that this is 630 meters because look, he's flying out and back over this point, okay? So he's doubling his movement over this section, which means the length of just this section has got to be half of whatever the remainder of 1,440 minus 810 is, whatever the difference is, 630. I simply divide this by 2, and I end up with 315 meters. Now, is that question ever going to come up, or is something ever going to come up on the physics Regents like this? No, probably not. Okay, let me move this over so you can make sure you see. No, probably nothing like that's ever going to come up on a physics Regents. But physics is all about problem solving, and building your problem solving skills is always a good thing to do. So this is a tricky question. But it's something that I think if I were to give you some time to work on it, you guys could all work out. Maybe not on your own, maybe in a group, maybe on your own, but it's an interesting problem. Physics is all about problem solving, and I thought that was kind of a neat thing to show you guys. So, we've gone over the difference between speed and velocity. Our next video will be on the difference between average speed and instantaneous speed. I'll see you for that one later.